think in this process how we can use key competences to support innovation and entrepreneurship, starting from the national qualifications framework down to program level in a very systematic way. So that is what I thought, as I said, at the national level, starting from general descriptors down to more operational way, we can embed the learning outcomes that we would like to achieve from the learnings of the programs. So I think I am not sure if I have exceeded my time, but I know that it took much longer than I expected, and I would like to thank you for your patience and listening. Thank you very much. Would there be any question period or environment, or I don't know how it is going to proceed? Okay.
Dear professors, I want to thank on your behalf Professor Durman for his speech. I am very delighted to invite Dr. Pat Patterson from NASA on giving his presentation on innovation and engineering education. Please, Professor. Do we need a presentation?
Yes, I need to set this up.
Okay. Go out here.
I don't want out. I want this. And then I want, here we are. All right, thank you. Hello. This is exciting. I am really, really impressed with the level of energy and innovation and excitement that is accompanying all of this work. And I'd particularly like to thank Professor Nader Nada, who has obviously done a great deal of work here, as well as on his innovative research on innovation. And I look forward. I've known Nader now. I could say bad things about you, Nader, but I won't do it. I've known him now almost 20 years. So it is a pleasure to be here and an honor. I was terrified, though, when I realized what Dr. Nada had asked me to do. Dr. Nada asked me that since I retired from NASA, we believe in retiring early and often. And so I retired from NASA last year, and he asked me to reflect on my career, and I thought, oh, okay, this will be the easiest talk I've ever given. So I started reflecting on my career for several weeks before I could even put the first word down on a piece of paper. It was very intimidating. And I realized that what I needed was more structure. So I reached back to a fellow named Ralph Stogdill, who was doing work like this in 1966 when I was just a little kid. And in fact, he's passed on now, and he's been gone so long now that Bernard Bass is putting his name on the book without Stogdill. I see. But in any case, Stogdill is responsible for a structure that I'd like to hang this talk on. And so I've got to explain Stogdill's model before we go any further. As I said, it was a 1966 paper in which he introduced a model for organizations. This is sort of his highest level diagram of an organization. It has 3 dimensions: process, structure, and an interpersonnel dimension. This is an influence model. This is the way I look at it. I apply it to an engineering team. And an influence model means that wherever you are in one of these 3 areas is going to determine how much influence your ideas get in the workplace. And particularly in an R&D environment like NASA, where people sit around and argue about design decisions. That's their currency, is design decisions. And examples of design decisions, as I said, are system requirements or various levels of product design, process design, test design, deployment design. We had a professor, Richard Evans, once who talked about design. I thought he had gone a step too far. But design decisions are made by people in the engineering organization. And addressing Stogdal's model is a fruitful approach to understanding how these are made. So let me change the model just slightly, and let's look at the part of it that said structure. Every organization is going to have a structure, and it's represented by the org chart, of course. If your name is on this chart, then somebody is your boss, and you are probably somebody's boss, or possibly both. And this is the subject of management training, which is performed in another part of the NASA organization. And besides, I'm an engineer. My first project at NASA was software on the Space Station Freedom program, which you may remember being canceled just prior to them turning it into International Space Station. I have some feeling of pride for that. I got the opportunity, though, at that point to develop what we called the NASA Engineering Training Program. And what a privilege. I was privileged to do this, but very quickly got kind of nervous about this. If you think about the job itself, I'm going to do engineering training for engineers at NASA. This is kind of daunting in a sense. We didn't even know what was wrong with engineering at NASA. In fact, just the thought, putting forth that thought was sometimes not a good idea. But in any case, let's get back to Stogdal. Although engineers are managers, there's a fundamental difference in the direction you're looking in the org chart. Looking at the idea of design decisions, a great deal of emphasis is placed on cost and schedule if you're a manager. I heard someone on the bus this morning talking about politicians, and they said, well, all they want to do is get reelected. Well, all managers want sometimes, it seems, is to control cost and schedule. And this gives a kind of a biased look at things. It seems impossible to think of systems engineering without thinking of emergent properties of design decisions, emergent properties of systems based on design decisions. When they present themselves as knowledge, the engineers are thrilled, as you might imagine. This is new knowledge, or at least it's new to me. And it's interesting because it's the stuff I'm working on so hard. A manager can look at the very same thing, though. And what does it look like to a manager? It looks like changes. it looks like corrections of something that was done that was expensive in the first place, but now it has to be fixed or it has to be redone. Managers can look at that and say, this is not a good thing. We don't need to be challenging our designs so much. This is just a fact of life. Now, if the change represents a change in technology, then it also represents risk. And a change in technology can almost be defined as, I've never done it before, me. Because that's basically where all the action is. It's with me, it's with the engineer, it's with the designer, with the people working next to each other. You know, it's not, well, it does represent risk in any case. At NASA, we have something called technology readiness levels. I think there are 10 of them, and if something is just thought up, you know, we've just come up with some new substance, our new thing called unobtainium. That's one of the NASA things that we never can seem to produce, unobtainium. In any case, I don't really know where I was going with that, so I will drop that. Excuse me. I'm very nervous. You can see, Nader, you've really daunted me here with this kind of task. As I said, we'll be talking about that. I believe that's a significant problem. And the problem gets worse. As Stogdill points out, the org chart is, as I said, only one influence factor in an organization. The organization's own process, excuse me just a moment, the organization's own process, its life cycle, the how-to of each process, may not be something that's very widely understood. For example, this is a rather complex system that we just decommissioned. The life cycle next to it is no simpler than the vehicle. They're both, you know, examples of very, very complex systems. And in the complex products, such as a jumbo jet with more than 1 million parts, or something like the space shuttle, understanding the entire product system in detail is just impossible for a single person, or even a single group of people. Now, a functional diagram for a complex product system can contain arbitrarily many subsystems, each requiring its own specialties, and each specialty likely operates with different processes and tools. To cope with this complexity, an engineer's scope, including the domain of authority that he works in, is necessarily reduced. It's absolutely essential to know where your process inputs come from. And it's absolutely essential to know where your output goes and what's going to be done with it. The purpose dimension is utterly important. Without this knowledge, an engineer is likely to jeopardize the integrity of the system by not understanding his own contribution to the system fully and simply making it like the last one he made. At NASA, we don't do things twice, generally, except for launching the space shuttle. I think that was its downfall. We did the same thing 100 and some odd times. But in any case, it's not actually a downfall. It's a prelude, I hope, to something bigger. And by the way, while I'm talking about this, let me make the point that this is not a NASA presentation. This is a presentation by me, and because of that, the freedom to say what I think is implied, I think. Well, often I believe problems could be avoided in engineering if engineers had increased knowledge, or at least better visibility, into other subsystems, not just the one with the immediate responsibility. Now, what about systems engineering and the concept of a chief engineer? Basically, the chief engineer has been proposed as many times for the cure for this visibility problem. Give the chief engineer, or more generally the systems engineer, X-ray vision, like this comic strip character has, who can see problems. This is literally how the chief engineer at NASA position was described to me as it existed back when people like von Braun were running NASA years and years ago. The chief engineer would be someone who could see around corners, see through products, and immediately find problems and fix them. It's a wonderful approach, but how many of these people will we need, and where will we get them? Some engineering organizations have ameliorated this problem through carefully planned forced rotations of engineers through different jobs. After several rotations, the engineer has a much better understanding of the system overall and can make local decisions in a global context, which is really the key to a systems approach. For example, a mechanical engineer who has spent some time in the software discipline will gain major insight into the system control structure. As another example, any engineer who spends any amount of time in the budget office is likely to return a completely changed person, especially at NASA. All of these considerations are above our pay grade, however, because we can't assign people to different jobs and make them do forced rotations. Our program at NASA was called NET, NASA Engineering Training Program, and one of our core beliefs was that every engineer has the responsibility for the entire system, even though the scope of one's actions is bounded by the organizational structure. So how can I have responsibility for the whole system, but I can only do what's in my little circle of influence? So that's the problem that I had to deal with. We did a study that we referred to as the Crossman study at NASA that interviewed engineers and managers very carefully. This guy's a psychologist, a PhD, and he came back with the answer that what engineers thought we needed was better teamwork, leadership, and communication. More of that in a minute, but let me assure you that that's so general that it's not really very helpful. But nonetheless, I didn't know that. I'm an engineer, not an organization expert. So I thought about it and thought about it and thought about it and actually assigned meaning to these things. At NASA Marshall, which is in Huntsville, Alabama, our office, which happened to be at headquarters in Washington, was able to work with the engineering office to create a course that they named the Comprehensive Systems Skills Initiative, which is a terrible name. Nonetheless, it was amazing because it's the only program that I know of that actually generated grassroots participation and excitement. People couldn't wait to prepare presentations on their part of the system. And we're going to get into this just a little further in a minute. But basically the idea is that you start with how many disciplines you have at a NASA center, or an engineering company would be the same example, or maybe even a clothing company. I don't know where you would stop with this idea, but you look at all the different disciplines. And that's not as easy as it sounds like. We started out with hundreds, and we had working groups that reduced the number down to 70 or 80. This is still a tough problem for training. How are you going to train 70 or 80? So the number got reduced by combining things down to about 20 or 25. Even further, as you can see in this particular list, which is a short list, but you can see all of the potentials. These look like circuit boards, and the idea is to imagine interrelationships between each one. But in fact, they really are complicated. Each one of these can be degenerated into another stack model almost, so that it can get very, very complex. This was done by a fellow named James W. Parker at Marshall. As I said, even managers as well as engineers were excited. The job was that they were going to take their particular discipline and develop a course around how they do it. They're going to talk about how I do this job at NASA. Not how it should be done according to a textbook, but how I do it. And for each one of these, essentially, discipline experts would be talking to general audiences about their process and drawing heated and actually this is fun criticisms from the floor from people who said, that broke my process, what you just did. Why did you do that? Another fellow might say, that put me back 2 years because you were playing games in the budget office. That's when the budget office talked, and a director of engineering actually stood up and said that. So they're debugging at the system level now, a process that actually couldn't even be addressed before very well, except by more general education, which abstracts things, of course, way above one's own job with the details and the experience that goes with it.